in conjunction with EEG to predict response to escitalopram. First of all, I have no conflicts of interest to declare. So we'll have a couple of objectives that we'd like to go over before we go into more in depth around the background around the paper. First off, I think it's important for us to have a basic understanding of how machine learning works. So we'll go over the history and some of the basic principles of machine learning. We'll tie that into psychiatry, specifically within the field of precision psychiatry. This is a burgeoning field that's only been possible to do this within probably the last couple of years at this point, and it's still a very, very young field. We'll also look at the study's methodology. We'll examine what machine learning algorithm they chose to use and why they chose it. We'll also look at the model that they ended up making, and we'll see how well it did in predicting response to escitalopram. Then we'll go over kind of the broader implications for this study and how this could be tied into clinical practice in the near future. So just to define some basic terms, artificial intelligence is a fairly broad term. It really just means a machine that can replicate anything that a human can do. And so back in the day, computers used to be people. People actually had to sit down and write down calculations, but they've been replaced by machines. And we call those machines computers now, but again, computers used to be people. And so that's a form of artificial intelligence. Your calculator and your phone is a form of artificial intelligence. It was something that a machine used to not be able to do. A human was only able to do it. And since then, well, at least human calculators have been replaced by the machines. Within artificial intelligence is a smaller field called machine learning. And this is where we see more of the sophisticated methods that are being used in some of the technologies that we see today. Even deeper within machine learning is the field of deep learning. And this is where we see very complex neural networks. So I'm sure many of you are familiar with ChatGPT. They use deep learning techniques to create ChatGPT as a system. And a lot of different tools that are being developed right now in medicine, specifically in radiology, and their use of artificial intelligence use deep learning models, but they also use some other machine learning models that aren't necessarily neural networks. And so machine learning isn't just artificial neural networks. There's a couple other methods that can be used, and we'll go over some of those things later. So just a brief history about the history of AI. Really the field had some of its beginnings around the time of Alan Turing. He was a British computer scientist. I would say this the father of computer science as we know it today. All of the coding languages that we use today in software are based off of the principles that Alan Turing created. Around his time, he conceptualized the idea of machines that could think like humans. And the Turing test is a test that if a machine is able to pass, means the machine is indistinguishable from a human. And so that test is named after Alan Turing. But it's really at 1956 that the term artificial intelligence really comes into the lexicon, at least in our modern day conception of artificial intelligence. It was crafted at the Dartmouth workshop. This was a summer conference that took place on the Dartmouth campus. It brought together mathematicians, statisticians, technologists, computer scientists, and they started to work out what are the things that we need to do to actually make machines that can think like humans. But following that, we start to see optimism, a lot of investment, venture capital, a lot of money goes into the field. There's a lot of hype. And what we see is actually two boom bust cycles. So hype, disappointment, investment leaves because people realize the technology is simply not there yet. We're actually in the hype cycle right now. And I suspect we'll have what's called another AI winter probably pretty soon. The picture on the screen is something called a perceptron. So back in the day, they actually had to wire neural networks together by hand. Now they're all stored in silicon, and in terms of they're just ones and zeros, and we play out the neural networks on GPUs or TPUs. But back in the day, you actually had to wire these things together. And so you can imagine when we have neural networks as large as ChatGPT, which has an equivalent number of neurons as the human brain. Granted, not as complex as the human brain. It would just not be feasible to wire those together by hand. And so what we really see is in the kind of the modern day, really after the 1990s, we're getting more capacity to store memory. In the 90s, you had a couple of megabytes and some floppy disks. But now I can store multiple terabytes in the palm of my hand. And so we've come a long way since the 90s. It's really within the past several years, we're seeing a lot of different techniques come out, different research papers from Google, who owns DeepMind. We have OpenAI, which is the company that made ChatGPT. They're also implementing a lot of innovations in the field. And deep learning has kind of been the I guess it's the most popular method right now, but it doesn't mean it's going to be the most popular method going forward as artificial intelligence continues to progress. So how does machine learning or AI work exactly? Well, the foundations at its core are based on mathematics and statistical principles. These include probability, algebra, calculus, statistics. They help us understand what data even is, what is the nature of data, and how do we use that data to make predictions or decisions. So things like the mean, the median, the mode, standard deviation, these things help us understand how the data is distributed. And then there's more advanced concepts such as gradient descent that are crucial for optimizing machine learning algorithms, specifically neural networks. Really the core of machine learning is really having an algorithm that can discover its own algorithm to solve problems that we throw at it. Instead of explicitly defining the instructions, we have the machine make those instructions based off of the data that we provided. So for example, in medical imaging, you can provide a set of training data, let's say x-rays that have been labeled with tumors versus no tumors, and the model is able to craft its own algorithm that can match the one that was labeled by the radiologist. You can subdivide machine learning to supervised versus unsupervised. So supervised learning means you have explicitly labeled the training data. And so let's say going back to the x-ray case, we have explicit labels of no tumor and tumor, and then we have the actual images. So those are explicitly labeled. Unsupervised learning, you're giving algorithms massive amounts of data that have not been categorized. And that's mostly because there's too much data for humans to categorize, or we don't know how to categorize it properly. And so these algorithms look for subgroups or different types of clustering within the data. In order to start using machine learning algorithms, you really have to start by framing the problem exactly. What are you trying to optimize for? You have to make a question. What are you looking to do? What are the variables that are going into the question that you're looking to answer? What are the forms of data that are available? Is it even possible to obtain the data in a way that can be used in a programming language? So an example could be if you're trying to create a machine learning algorithm that can predict readmission rates, that would be considered a binary classification problem where a patient is either a 30-day readmission or they are not a 30-day admission. And the variables you might be looking at are the different medications they're on, their comorbidities, different types of surgical procedures that might have been done. So those are some of what we call features of the data. And the output of that data would be the 30-day readmission versus not 30-day readmission. Then you have to collect the data. Having a robust data set is incredibly important. If you don't have good data, you're not going to have a good model. It's pretty simple. But getting the data is not so simple, especially in healthcare where you're dealing with electronic medical records, which are not optimized for data science, unfortunately. You also have issues around privacy that also come up when you're trying to collect massive amounts of data in a healthcare setting. Then there's data processing. This is probably the most annoying step of machine learning. I've gone through this process. I've made some machine learning models myself, and cleaning data is probably the most annoying part of this whole process. You have to make sure the data is streamlined and cleaned, and it's set up in a way that the programming language actually is able to understand what you're looking at, or actually what it's looking at. Data preparation, you're just essentially placing the data into what we call a data frame, and that's able to interface with different, what we call packages within specifically Python, which is the most popular, but you can also utilize MATLAB. You can use R for some machine learning models as well. And this is where you have to translate certain variables. So let's say one variable is categorical, like male, female. You have to categorize that, you have to frame that as a numerical value so the computer can understand what it's looking at. And then you have to scale things, normalize things based on the assumptions of the underlying model. And then you train the model, and this really depends on the model that you're using. But essentially, you're giving the data to the model. It's able to correct itself in order to actually match the output that is present in the training data. And then you evaluate it, you can tune it. How accurate is the model? What are some things we can do to tweak the model? There's a number of different methods that are beyond the scope of this presentation. So we can kind of go over some of the things that we have to consider with the actual foundation of a model, and that's data. And so it's really important to have a good understanding of this, especially as you're going through looking at the literature. As we have more studies in precision psychiatry that come out, we have to have a pretty skeptical mind about, well, do they have the proper data to actually make the conclusions that we might think that they're making in their paper? And they'll give those caveats, but we have to be aware of those things. So the biggest assumption is you have enough data. And so here's an example that can illustrate that. So you're trying to map reality. You want to make a model, which is essentially an algorithm or a function. And so this is the data that you collect based off of this data. This is the prediction that you make. Your model gets 100% accuracy. Based off of the training data, it's able to perfectly map it onto this particular function. But as you collect more data, you realize actually it's a little bit more complex. You're not really getting the big picture with the data that you had before. And so what you get is that your model does not map onto the reality. And so your predictions are not going to be robust, and they're not going to match on to this supposedly 100% accurate model that you had just made. So let's go over some of the simple methods that you might see, and we'll kind of get more and more complex as we go through. So logistic regression. This is a model for binary classification. It's useful in medical settings for risk assessment, early intervention, treatment planning. Core idea is to estimate probability of a particular event happening. So disease onset based on one or more prediction variables. So age, blood pressure, these things could go in as contributing factors. So other examples like diabetes, you would add in age, BMI, blood glucose, A1C, stuff like that. And then the model would classify the person as diabetic or non-diabetic. So your output from using this algorithm would be a probability score. So if you have a probability score of 0.7, that would indicate you have a 70% chance of the event occurring. This is probably the more interesting machine learning model. And again, like I mentioned before, ChatGPT uses it. A lot of image recognition software uses this. If you go into your phone, into the Photos app, and you search cat, this is actually the model they're using to identify what a picture of a cat looks like. So neural networks, artificial networks specifically are based off of the human brain. So we have individual neurons, and it's actually a pretty simple foundation. You have one neuron, has a series of inputs. It adds these inputs together, and if it's above a certain threshold, the neuron will turn on. If the threshold is below, if the addition is below that threshold, the neuron stays off. Now, by itself, it doesn't seem that impressive. You know, the thing turns on or off, big deal. But when you connect them in tandem at multiple layers, you get incredible complexity. I mean, this is the complexity that gives rise to consciousness. It gives rise to behaviors. It gives rise to emotions. So it's very powerful as a tool, and it can do very complex things like image recognition, and it can replicate intelligence, as we see with ChatGPT. And this is really the foundation of deep learning. So I think it's important to know kind of the basics of this. There are different things that go into a neural network. So you have weights, and so this is the inputs that go into the neural network. So how strong are those weights? Then you have the bias. So how much is that threshold for the neuron to turn on? And then there's a concept called a gradient descent and backpropagation. And these are essentially methods, statistical methods, to adjust the weights and biases or the interconnections and thresholds of the neurons such that you can eventually match the output. It's a pretty intensive process. It requires a lot of computational power. And we've only recently been able to scale this. It's only within the last few years that we're able to make robust and powerful neural networks. The next machine learning method that you might see in the literature, specifically in the field of precision psychiatry, is random forest. So random forest is an ensemble learning method, and that makes a lot of different models. These are decision trees, hence the forest. You can do classification, you can do regression. You essentially create a ton of different decision trees, and you do this by randomly selecting from your training data. So you're not using all your training data all at once for one decision tree. You're grabbing random parts of it, and then you're making decision trees to optimize for those particular features and outputs based off of the random data that you selected. Having built one of these models, I mean, this is pretty computationally intensive. You can imagine if you have millions of data points that you're going to be making a lot of different trees based off of the different subsets of data. For one of the models I made, it took a full day for my computer to actually process all of the computations to generate it. But what you end up getting is each tree has its own output, and you essentially aggregate all the results, and there's essentially a consensus. And essentially that final consensus is more accurate than any one decision tree could be on its own. And it's useful to have a random forest because oftentimes in the example I mentioned before, you don't know if you have all the data. So you're making the assumption that you have enough to actually model reality. But because of the randomness that's introduced, and reality has some randomness built into it, you're able to have a more robust model that's able to kind of keep in mind that there might be different values that aren't necessarily represented within the initial training data. And so it's a pretty powerful method for breaking down large sets of data. The next machine learning method is k-nearest neighbors. So this is a machine learning model that makes predictions based on the closeness to known example. So this is a pretty unique machine learning model. It doesn't have a training phase. It's operating on a pretty simple principle. It'll make predictions about new data by comparing it to the data that you have given it. So I think an analogy would be if you're trying to classify whether a tumor is malignant or benign, you would look at the labels of other benign or malignant tumors that are closest to the tumor in question that you're trying to categorize. So the K in the k-nearest neighbor stands for the nearest neighbors the algorithm considers when making the prediction. So if K is set to 3, the algorithm will look at the 3 closest neighbors to the new data point that you're trying to classify. And choosing the right value for K is pretty important because it impacts how this algorithm will perform and how much computation is going to be required. So a smaller K makes the model more sensitive to noise, while a larger K makes it more computationally expensive. So you have a very high K, it might take a long time to get a prediction back. Like I said, there's no training phase here, and it can do classification and regression. And then finally, support vector machine. This is a model that we'll be examining in the context of the current paper. So support vector machine is a supervised learning model. So remember, supervised means you actually have to have explicit labels for the input and explicit labels for the output. And essentially what you do is you're mapping the data into a multi-dimensional space. So you can imagine in this picture on the left, you have one feature and one output, and you have 2 different classifications. And you can create a line essentially that separates it. And what a support vector machine does is it maximizes the margin between the 2 categories. Now, let's say you have more features. Well, then we can see the picture on the right. You can map it onto 3D space. You have 2 feature sets and then 2 categorizations. You can create a plane that will separate it. Now, let's say you have even more features. Well, then you're mapping this into multi-dimensional space. And this is why a machine has to do this. A human being can't even comprehend 4-dimensional spaces. And we're talking about thousands of dimensions, essentially. Only a computer could do that. And it is computationally intensive. We can represent these things as mathematical functions, and we can represent the mathematical functions into code. And so what we're doing here is doing a classification method that's able to maximize the margin between 2 different categories. And this is the one we'll be using moving forward in this paper. So AI can intersect with psychiatry in a number of ways, and it's been called precision psychiatry. It's a new field. There's a lot of hype around it. People talking a big game about big data and how it's going to revolutionize mental health care. I think that there's a lot of potential in physical health for now. There's a lot of cool things coming out in the world of cancer detection and risk assessment. But in mental health, things are a bit more complicated. So what we're dealing with are very heterogeneous disorders. Something like depression, we give it one label, you have major depression, but there might be many different subtypes, but it's scattered throughout the population and we don't know how to categorize it properly. And so what we could do is we can have different questionnaires for symptoms. We can have different psychological testing, IQ testing, genetic testing. We can have questionnaires for life experiences like ACE, the adverse childhood events. We can look at people's biomarkers. We can look at their neural circuits with fMRI, with EEG. Based off of all this data, we can create subtypes of whatever disease we want. Let's say depression. There might be many different types of depression, and there have been some studies that have looked at this problem. And then based off the subtypes, you can personalize the treatment for that particular etiology. And that's the goal of precision psychiatry. Is it there? It's not there yet. And there's a lot of challenges to bring precision psychiatry to a point where we can actually implement it in a clinical setting. There's a lot of questions around privacy. If my data is being used to train a model, is there any way this can go back to me? It's a pretty thorny issue when it comes to data privacy, especially in the field of mental health. But as we kind of progress and gather more data, the goals of precision psychiatry are becoming more and more realistic. Even more than that, there are other things you could do with precision psychiatry that aren't necessarily related to multiple different people. It could be just an individual. You can train a model based off of an individual's activities. Tom Insel, the prior head of the National Institute of Mental Health, did a lot of work with what's called a digital twin. You can essentially take data from someone's internet activity and see, well, if there's changes here, does that mean they're going to go into a manic episode soon? And so that's very individualized and very personalized. Large language models, these are the foundation of things like ChatGPT. We can imagine a system that is able to do CBT with an individual one day. That's certainly possible, and that's very personalized as well because it's meant for that individual and not necessarily for an entire population of people. And so the paper that we'll be discussing today is called, the title is Use of Machine Learning for Predicting Escitalopram Treatment Outcome from Electroencephalography or EEG recordings in adult patients with depression. It's by Zandov et al., published in 2020 in JAMA. I think it's important to frame why something like this is important. Why are we even doing any of this? Why are we collecting all this data? Why are we talking about these machine learning algorithms? What does it even mean? What's the importance? Depression, also major depression, also known as major depressive disorder or clinical depression, is a common and serious mood disorder. It's characterized by persistent feelings of sadness, loss of interest in activities that we once enjoyed, difficulty in performing daily tasks. It's pretty prevalent. About 21 million Americans will experience at least one major depressive episode. I mean, that's almost 8% of the population. If you get 100 random people in the US, 8 of them would have serious depression or clinical depression. It's a significant contributor to disability worldwide, and this has implications economically. We're talking about billions of dollars of lost economic productivity, people not being able to work, people not being able to participate in their families, and even in their lives. I mean, the impact on families especially is important. You can imagine a child who grows up with a mother who has depression that is not treated properly will have maybe some adverse childhood events because they have a mother who's unattentive, and this can lead to attachment issues and other psychological issues later on. So this goes beyond the individual. This affects every facet of society. And the United Nations, I think it's the Charter on Human Rights, they say that the family is the fundamental unit of society, and if family members are depressed, it affects society as a whole. But even more than that, it's the individual suffering. The person is not able to do the things that they want to do, and they aren't able to be the person that they want to be. And so just at an individual level, it's important to address depressions to reduce individual suffering. So, first-line treatment, at least medication-wise, is SRIs. But the way we prescribe these SRIs are fairly trial and error based. We don't really know if this particular medication is going to work for this particular individual. We gave them a label of MDD, but that's really how far we go. Ideally, a diagnosis should tell you something about etiology. It should tell you something about pathophysiology. It should tell you something about prognosis, and it should tell you something about treatment. Psych diagnoses are kind of limited in that regard. And so that's why a study like this is important. So the study utilizes EEG. We can go over kind of the basics of EEG. I'm sure we've all seen it. It's mostly utilized in neurology, specifically in seizures, but you can use EEG for sleep studies as well. There's no clear guidelines on the use of EEG in psychiatry. There have been studies on it, but there is no clear guidelines how we can utilize this in the treatment of just mental health disorders. Most of our experiences in the hospital where we have a patient who comes in who has a psych issue, but they also have a concurrent neurological issue, and that's why we would employ EEG. EEG will take different leads placed on the scalp, and we're looking at kind of the superficial outer part of the brain. We're looking at global brain activity at that particular part of that region. And so we're summating millions of different electrical outputs from neurons in that particular part of the brain. And then we have individual leads, and we hope that that can maybe create some spatial differences between the different parts of the brain. Again, this is all superficial, putting on the scalp. There are deep EEG leads that you can put in with very long leads that actually go into deeper parts of the brain. But that's outside the scope of psychiatry at this point in time, but maybe one day it might have some benefit. And there are also studies that show that EEG can predict antidepressant response. Again, this paper is kind of a build up to the ongoing literature that has shown this. So EEG and antidepressants have been studied. There's a number of studies that have linked some EEG changes and EEG features that are predictive of antidepressant response. So alpha and theta band abnormalities in resting state EEG have been identified as potential biomarkers for predicting antidepressant response. Specific associations have been found with the posterior alpha activity in response to fluoxetine, amitriptyline, theta activity with response to imipramine, venlafaxine, and various other SRIs. Delta activity with response to imipramine and paroxetine. Asymmetrical activity and frontal theta activity are recognized as neurobiological markers for antidepressant treatment response. Predictive models leverage these EEG findings, and they can also look at kind of broader activities, not just one particular wavelength abnormality in one particular area. There's global dynamics that can also be considered. There was a study done in 2020. It was looking at resting state and brain dynamics, looking at responders and non-responders for antidepressants in patients with major depression. This was a model that produced a 96.67% accuracy, but there's some caveats here. The reason why I didn't choose this study for this journal club is because it only had 30 some patients, and it was all from one site in Columbia University. So there are studies that have been done that are similar to this, but I chose this particular study because it was a bit more robust. So let's talk about kind of the design of the study. So this was a prognostic study using multivariate EEG data. They use the tripod reporting guidelines. This is just metrics and regulations, but some standards for reporting multivariate data when you're using machine learning models and research. Ethics approvals were done, informed consent was obtained, and data was sourced from another study. And this was kind of the bigger study that is the source of the data for this current paper. It's called the CanBind-1, or it's also called the Canadian Biomarker Integration Network in Depression. So this was a multi-site initiative aimed at identifying biomarkers to predict outcomes in patients with major depression undergoing antidepressant treatment. The objective of this study was to look at individual and integrated neuroimaging, electrophysiology, so EEG, molecular findings, and looking to see if that could be helpful in predicting clinical response to antidepressant monotherapy and actually even augmentation therapy in MDD. The study was actually over the course of 16 weeks. Protocol begins with an 8-week treatment phase where patients receive escitalopram from 10 to 20 milligrams. Based on the evaluation at 8 weeks, patients may receive an augmentation with add-on medication, specifically aripiprazole, for another 8 weeks. And again, this data was collected across various sites. This included neuroimaging, fMRI, genetic studies. Blood samples were also collected. EEG was collected. Patients would undergo neuroimaging and molecular testing at baseline. So this is week 0, at week 2, and at week 8. Then also at week 4, week 10, week 16. And then there were other clinical evaluations that would happen at week 16, week 12, and week 14. Treatment approach was if patient had at least a 50% reduction in their Montgomery-Åsberg Depression Rating Scale or the MADRS score, they would continue escitalopram for another 8 weeks. If they're a non-responder, then after the 8 weeks, they'd be started on augmentation therapy for 8 weeks. In terms of techniques that they used in this study, so the Combine 1, they used multivariate analysis, machine learning, and this was a multi-site collaboration. So you had 6 different academic centers. This was in university settings, research centers. Essentially, you were able to pool the data together and able to get kind of a broader picture of what was going on. The limitation with a lot of machine learning studies is if you stick with just one population, that model cannot be generalized very easily. And this is really the biggest limitation of using machine learning in psychiatry ultimately. So in terms of the participants of the study, specifically looking at escitalopram response, utilizing EEG as a prognostic tool, patients were aged between 18 to 60, and they met criteria for DSM-4 for major depressive disorder with a current major depressive episode. The resting state EEG was collected from 122 patients at baseline. So this was before the treatment was started with escitalopram. And then of this 122 group, 115 had EEG done at 2 weeks after treatment was initiated. And then again, treatment response was categorized based off of the MADRS score. So like I said, a reduction of 50% within the first 8 weeks is considered a positive response. If it's less than 50% reduction, that would be deemed a non-response for the study. So once the EEG data were collected, they had to be harmonized. So you had a lot of different findings from different sites, so 6 different sites. So they had to be kind of essentially consistent and clean and comparable to each other. So that's what the harmonization and pre-processing stage is for. Pre-processing was performed to remove any common noise, so like the 60 hertz power line interference. And this is, again, all this is done to make sure that things are standardized and can all be inputted into the machine learning model. So feature computation and ranking, we can collect a lot of different data, and EEG presents you with a rich source of data. You have tons and tons of stuff going into an EEG. But what happens when you make a model is if you put in all this stuff, it can slow down the model. It can make it very hard to actually get anything done. And so ultimately, what you have to do is identify what are the big things that contribute. So if you have 10 different variables that are contributing, at least that you think contribute, and then through just very basic statistical t-tests, you find that maybe only 5 are actually have any sort of significant impact on the outcome, you can remove the 5 that don't necessarily have any sort of impact as far as you're aware in order to improve the efficiency of the model. That helps with training, that helps with just streamlining the process of creating these algorithms. And so you have to identify specific data points that could help in predicting the treatment outcome in this case. So selecting the most significant data points from a large pool of data is a pretty hard task, but there was a framework that they used in this paper. Various EEG features were evaluated, including traditional electrode level frequency analysis, power spectral features, spatiotemporal complexity, global brain network dynamics. So electrode level frequency analysis. This is, we have electrodes placed on the scalp to pick up these signals. It just means you're looking at how often these signals are happening at that particular electrode. Power spectral features. This is about breaking down the electrical signals into different frequency bands. So remember the alpha, theta, delta, and understanding their strength or power. It's a bit like tuning into different radio frequencies, and you can hear different music in those frequencies. Spatiotemporal complexity. This is about studying how these signals change over time across different areas of the brain. And so it's looking kind of at the brain's overall complexity. Then global brain dynamics, network dynamics refers to how different parts of the brain are connected and interacting with each other on a kind of a larger global scale. And so 4 different features were essentially defined. And within these features, you have tons and tons of sub-features that you're actually inputting into the model. but the subfeatures include electrode level spectral features. So again, similar to electrode level frequency analysis, that's the frequency at the electrode. Source level spectral features. This takes a step further and try to figure out where in the brain these signals are coming from. So this is more from a source perspective. Multi-scale entropy features. So this involves looking at the unpredictability or randomness of the brain signal at different scales. And that gives insight into complexity. And then micro state-based features. These are short periods of stable electrical patterns in the brain. And so from this, you have a very, very large set of features, essentially, that you're going to put into your model. They used a filter-based method utilizing an unpaired two-tailed t-test for feature ranking. So ranking which ones are the most important for actually determining the outcome. And they had a certain threshold, about 60 votes, in order to actually include it into the model. And so the model they ended up using was a support vector machine. Has specifically a radial basis function, or RBF, kernel-based support vector machine. It was used in this study for a couple of reasons. Support vector machines are known for they're pretty well known for their ability to help categorize data in EEG studies specifically. They have a lot of history in the scientific literature, especially with the ability to handle high dimensional data, such as EEG studies. We're dealing with like hundreds of thousands of features, essentially. And so being able to map that into three-dimensional space with a support vector machine helps with categorization. It's able to handle a multitude of different features from the EEG data with different types of statistical tricks that are beyond the scope of this presentation. And again, the goal was ultimately to split the group into responders and non-responders. And so this is a pretty good model for this type of binary classification task. And it's also able to have a balance between sensitivity and specificity. Remember, the support vector machine maps the data into multidimensional space and tries to maximize the boundary between the two different groups. And so that helps you balance the sensitivity and specificity when you're making this type of model. Also, support vector machines can be cross-validated. We'll talk about that a little bit later. But essentially, you're able to kind of test the model for internal consistency and to make sure that the model is not overfitting. So essentially making a model that's too close to the data and not able to be utilized in a setting where you're going to put in new values that the model didn't see before. Just practically speaking, it's just probably the best thing for an EEG-based study, just based off of what has been done before. And so if it's not broke, you don't have to fix it. One of the things they also did here is they left one side out for cross-validation, and we'll talk about that a little bit later. So the demographics that actually partook in this study, like I said, there was 122 people, 76 females, that's about 62.3% of this of the participants in this study. Average age was around 36.3 with a standard deviation of 12.7. Average MADRS score was 30.1. If you're familiar with the MADRS, that would be considered, the average would be moderate depression. Kind of makes sense. Standard deviation was 5.8. There was a subset analysis. Remember, 115 patients of the 122 had post 2-week treatment EEG done. And this is a similar demographic distribution. And so what did this study find exactly? So before we go to the model, I wanted to find with just kind of the simple statistical tools that we have. So the primary feature was the multi-scale entropy, and that reflected the complexity of the EEG signals. There was a tight cluster of predictive features around time scale 17, different feature patterns observed at baseline at week 2. So there was kind of a difference there between those two different time periods. In terms of secondary features, like spectral power features with specific bands showing some predictive capacity, actually. So high alpha and middle beta bands were prominent in baseline and at week 2 data. Theta and low beta bands were notable in early change features. So this is the 2-week data that we're collecting. And interestingly enough, the high alpha band power in the anterior cingulate cortex was a significant predictive feature for predicting a treatment response to escitalopram. So how did the model do? After all is said and done, you got all this data, you cleaned up the data, you refined the data, found the most impactful features, and you actually put it into the support vector machine model, and it created a new algorithm. Essentially, the final output showed an accuracy of 79.2%. How do we get that number exactly? So one method that is used in machine learning model validation is you essentially take 90% of the data that goes towards training the data. It can be 80% sometimes. But in this case, you're taking 90%, you're training the data, you leave 10% out, and then you test the model that you made on the data that you left out. So you can essentially do that a couple times, and then you can average that and you can get the actual performance. What this study did, which was interesting, is they left one clinical site out. So this was a clinical site that collected data, but none of that data went into actually training the model. And so this is very novel. I mean, this is a novel set of data that the model has never seen before and it was not trained on. And so this is a very good way to see, is this model actually predictive of real world data? And so this is why this is a pretty good study, is because they had that in their methods. And so with baseline data, so at week 0, before they got the escitalopram, the accuracy of the model was 79.2%. And so with a 79.2% accuracy, you could predict whether or not a person, just based off of resting state EEG, before they even get the medication, whether or not they were respond or not. They made another model with, again, 115 participants where they collected the baseline EEG, but then also 2 weeks out from starting the treatment. And this actually showed an improvement to the model's performance. So a couple percentage points, 82.4 of the specificities and sensitivities listed as well. Interestingly enough, at the 2-week model actually has a higher sensitivity compared to the original model. And the accuracy is actually pretty similar between the leave out site. So again, this is novel data, and then the tenfold cross-validation. So cross-validation is when you essentially have the 90% that's for the training, 10% left out, and then kind of going through that process essentially 10 times. So tenfold is you're doing that process 10 times with 10 different separations of data. And so what are the key findings here? So the study demonstrates the potential of using resting state EEG to predict treatment outcome with escitalopram specifically. But it should be noted that the prediction was regarding treatment outcome. This is not about individual response to the medication. You can look at neural dynamics by EEG, and you can even see the early changes at 2 weeks, and that does increase the accuracy of the model. And so there might be a role to actually have the baseline and then also a follow-up EEG to actually see if this is going to be an effective treatment for someone, before they start having all these side effects that people complain about. We can try to avoid some of that stuff. This is a pretty interesting study because they left that one side out, and they're able to see that the model was pretty effective. Even though the model never saw that data, it was still able to have pretty good predictions. And the study was also able to find some new EEG features that weren't previously documented in literature, such as asymmetry and the complexity of neural activity between hemispheres. That's actually was found to be one of the predictive features that could predict response to antidepressants. So there's some new stuff that was also found with the study. But what are limitations here? So this is an open label study that does not have a control group. So there's no way you can probe causal relationships here. Despite the fact there was cross-validation, again, there was tenfold cross-validation. You did this process 10 times. You did feature selection. You have a leave out site, so one site that didn't go into the training model. You're still dealing with a small sample set. When we talk about machine learning, we're talking about oftentimes millions of rows or individual cases. This had 122 cases. And so this is really kind of going into the problem of using machine learning in psychiatry. The fact of the matter is, given the complexity of mental health and the heterogeneity of mental health, you need to have incredibly high numbers of people actually providing their data into the model, and actually has to be constantly updated over time. 122 is not enough for something like this to be generalized across the whole population. In order to do that, and again, this is probably something that may happen in the future, you'd have to have probably most of the academic clinical sites in the United States recruiting patients to build a global model, to make a model that's applicable to US citizens. An endeavor like this is incredibly expensive and time consuming. And if it could only be done at a federal level, you'd have to have the NIH actually organizing this. Whether or not it's feasible, I mean, I just don't know. But it's something that would have to be done if we actually want to utilize things like this in clinical practice. And so there's a lot of stuff that needs to be overcome before a paper like this can actually be applied to a clinical practice. And so some things to consider as we wrap up this presentation. So
Yep. All right.
how might we consider the additional variables into a model? So this particular paper just used EEG, but the original Combine study collected a bunch of other data, genetic data, fMRI, different questionnaires. This probably might be able to be done now. There's a recent innovation in neural networks with transformers, but this we use to support vector machine, which is a different model. So maybe there's a case to be made that we have to make we have to kind of change our paradigm with how we're looking at treatment response to antidepressants and move away from support vector machines into neural networks and implement these other kind of inputs, including people's traumas. There might be a way to quantify that in a way that can actually inform a model. The actual steps towards clinical translation, like I mentioned before, we need to have much more data. 122 is not enough, but if you look at the other studies that use EEG to predict antidepressant response, they have maybe like 30 patients. It's just not enough to generalize across a whole population of people, especially with such a heterogeneous disorder like depression. If there are different subtypes, if out of 30 people, you might only have 2 people representing a certain subtype, and that's just not enough. And another question is, in what ways might this model be tested and refined in randomized clinical trials? That's something that I think we'll have to consider as people start utilizing AI in psychiatry a little bit more. And so those are things that could happen eventually. All right, that's the end of my presentation. Any questions?
So thank you so much for the presentation. That was really, really neat stuff. If you were able to scale this up and have more participants and say potentially have a placebo arm, could you use the data from placebo responders to, I guess, match with Lexapro responders as well and kind of take out that data from people who respond to Lexapro and therefore get people who have MDD who actually need Lexapro? That sounds pretty neat if that would be possible.
Yeah, I think it's possible, but like I said, the issue is recruiting enough patients to actually do that. Because I mean, just recruiting patients who are going to get it without a placebo is hard enough. When we have the placebo, we're kind of looking at more of a causal relationship. This study was more looking at predictive power, if that makes sense. But I mean, what you're describing is certainly possible. And like I said, in the future, I think we'll have to incorporate other pieces of data. EEG is probably not going to be enough. I think we'll probably have more rich sources of data to inform that model. But yeah, I think that's really the future direction, is having the system in kind of parallel with a placebo arm to kind of inform the model a little bit better.
Nice. That's very cool. Thanks so much.
Hey, Ryan. My bad. Ask a question real quick.
Yeah, go ahead.
So first off, I thought it was a really good presentation. I feel like this is something that, it's a very complex topic. So I appreciate you trying to explain it best you can, because it allowed me to, who isn't very familiar with this, to understand it a little bit better, especially computer modeling, which I'm not familiar with at all. One thing I would say is, like, obviously you kind of touched on this in a bit, but there's a whole maybe not necessarily ethical, but kind of like philosophical question about how this affects psychiatry and how this affects our clinical decision making. How, especially like how we don't want to give up our ability to interact with people and using machines and computer models to diagnose and treat. And I think you kind of mentioned that we're not really there yet, obviously. Like, this is going to, psychiatry itself and mental health is a very complex topic that can't just be measured with the current tools we have. My one thing is, how do we, as we make these models, how do we keep bias out, basically? Like, especially unconscious biases, because if you just put numbers into the system, obviously other biases can come up, as in, racial biases, age biases, those other things. Like, I know this isn't necessarily dealing with this paper, but for larger treatments and for larger diagnostic principles, for instance, African Americans, for instance, are much more likely to be diagnosed schizophrenic or bipolar, when in reality, maybe sometimes those are people who are dealing with other issues rather than actual psychotic symptoms. Can you touch on that at all, or anything you've
Yeah. Yeah, you're totally right. I mean, there's a philosophical backdrop to using machines to essentially interface with consciousness. We do that. We're conscious beings, we interface with other conscious beings, and we live in a broader society with different ethical principles and different biases that exist based off of our history. And unfortunately, these models will capture that. They'll capture all of it. You can imagine, if we were in a society that had kept homosexuality in the DSM, that was in the DSM at one point. It was totally feasible that maybe someone could have made a model that could have put someone into this disorder. You have this disorder or not. And so how we even conceptualize disorder has to kind of be interrogated at this point. But unfortunately, the thing is, our biases will be captured. And that's really one of the big issues with these models right now, is the biases are reflected. These machine learning models are like mirrors. They're mirrors onto society. They're mirrors on, and the data is a reflection of society, essentially. What are the things that are important for us to categorize? What are the important things for us to actually document and put into ones and zeros that we can feed into a model? And so this is a hard issue. It's often discussed in AI ethics courses and AI ethics conferences. There are actually conferences on AI ethics. And this is something that is brought up. Racial bias is reflected in a lot of AI models. An example might be, this is a very glib example, but when Google was initially training their machine learning models to classify like dumbbells, when it was making the image, you could reverse essentially the process to make an image. The dumbbell would always have like a disembodied arm attached to it. So think about that. The thing that we're presenting to the model, essentially we're associating the arm with the dumbbell. You didn't give it enough examples of the dumbbell separated from the arm. And so you can see how this might be, this could translate into like, different racial biases, different historical biases, and that gets attached to different disorders. It's hard to separate those things. But yeah, it's a difficult problem. I don't think it's going to be solved anytime soon, but if we build these things, we have to have the at the forefront of our minds.
So you're saying is basically we have to change our society before we can change the AI models?
That's right, yeah. Because the AI is just a reflection of our society. That's all it is. It's just a reflection.
Thank you.
Yeah, I did have a good discussion with Dr. Malik before coming here, because we're both working in EPS right now, but we had a kind of a discussion around diagnosis and how that kind of may play into this. And so one analogy that I think we had come up with was this concept of shortness of breath syndrome, and how when we diagnose people, we kind of give them this label of shortness of breath syndrome. And depression, you have depression, but there's maybe different types of categories. And so as we kind of make these models, I think we have to be kind of skeptical around the way we're conceptualizing things in the present moment with our current DSM, and perhaps things will be different in the future. And there won't be just one major depression, there'll be different types. And so that's another consideration when we're working with some of these things. Are you properly labeling the data, first of all?
So I have a question, and it also is somewhat of a comment, maybe to help you think about this. Because I think you'd find it interesting. So I remember I had a patient a while ago that had hallucinogen persisting perception disorder. And I had done some review on it and realized that there was a doctor that was starting to look into specific EEG changes to suggest a response to lamictal or lamotrigine for it. And I don't know how much you've been following the recent dialogue on psychedelic therapy, but Stephen Stahl recently released a podcast talking about it, and he's extremely critical of it from the perspective he thinks that things like HPPV will be a huge problem, and that we don't know who's going to end up having that, and that could end up making the benefits of the treatment way worse because of people having flashbacks and wrecking cars and stuff.
Yep.
And so I wondered, you know, do you think that there's a role for machine learning to help with streamlining this kind of data so that we can get people that we would expect this to happen to, prevent them from being in the treatments, or even detecting it early and preparing them for that?
Yeah, it's a good question. I mean, I should preface, I have an interest in artificial intelligence in medicine, but you know, the more I learn about psychiatry, the more skeptical I am that we can properly apply machine learning in clinical practice in psychiatry, at least in this day and age. At least as we kind of move forward, like I said, the amount of data that you need to actually make something that has good clinical utility is absolutely insane. You need to have a broad swath of the population represented within the training data. And so when you're dealing with something like a consequence of a psychedelic substance, starting from the bottom, you have to really kind of have a lot of foresight into how you're building it. You know, once it's regulated and legalized and FDA approved, you have to have, you know, certain maybe REMS protocols where you actually get some of this data and it's streamlined and standardized so that we're building this data set over time and it's done in an intentional way. So it might be possible in the future, but we have to be very intentional about that from the very, very, very beginning. And we have to understand, like, well, I mean, it's not just that. I mean, there's a guy that was on an airplane who tried to shut off the engine because he did psychedelic mushrooms and became super dysphoric. He wasn't tripping on the airplane. He had a dysphoric reaction. And so we have to find ways of categorizing that in a way that is captured by data, in a way that can actually be put into a model. But we have to be intentional from the very beginning once these things are regulated so that we have means of capturing the data, ways of standardizing it in a way to actually represent the whole population. So it's just a very hard thing to do. Whether or not we can do it, I don't think so. I don't think it's going to happen.
No, thank you. I think that's a very fair answer.
All right. Any other questions, comments? All right. If that's it, thanks for joining, everyone. I'll end the presentation here. Hope you all have a good day.
Thank you.
Thank you.